Thank you for having me here today. I'm here to talk about AirMettle's real-time smart data lake and how we're extending it to support accelerated in-place analytics of scientific data. So AirMettle's developed a real-time smart data lake that actually does big data analytics literally within the storage layer itself. By implementing it within the data storage lake, it enables us to perform basic analytics before any of the data touches the network. So it's significantly. Yeah, like let me see if it works. What patches? One. That one has a clip.
Yeah, let's try this.
That one already. Yeah. Okay, does this work? Okay, sorry, much better. Okay. Okay, so by processing within the data lake itself, it enables you to substantially reduce the network traffic because the vast majority of these big data analytics only needs a tiny portion of the actual content that's within the original object. By enabling you to do real-time operations on that data, it enables you to effectively take any of the data within your data lake and analyze it effectively on demand, as opposed to needing to load it into a completely separate tool like a data warehouse. And okay, we've been honored to receive both a STTR from the National Science Foundation, and the result of this work enabled us to get our first customer, which is Los Alamos National Labs. The work that I'm going to be talking to you about that relates to HDF is related to the work we've done under awards from the National Oceanic and Atmospheric Administration under a pair of SBIR awards, the second one of which was just commenced. So say like when people say like it's a data lake, what exactly is a data lake? So when people load data, of course, we know that some form the data is internally stored in some kind of a parallel storage file system of some sort. But what exactly is that? And it's important to take a look and say, what does that mean? Well, most data, when people talk about it, they see it's either structured, which they mean loaded into a particular database of some form, or people say that it's unstructured. I disagree. Like, in fact, this entire group here about HDF, like it is a format for a file specification and things that work around that. So a lot of data that is collected and stored isn't some random white noise. It's actually collected and stored in some semi-structured data format. And there's a wide variety of them, which is CSV, JSON, videos typically in like MP4, H.264. That spec defines over 90% of the video on the internet. Everything from cat videos to like news and like all sorts of stuff, like even professional movies. And so what can we do if we know that data has some semi-structured format? So this is very different from like completely unstructured white noise that you can't do anything with, or like it's really not in a database. So this data is like actually typically right now it's stored in this distributed system, and it gives you the ability, you don't have any hotspots whenever you're going to read data or write data. But unfortunately, you really either, if you're going to process the data, you either read the entirety of the object up to some higher level tool, or you have a large number of very tiny reads and writes to get to this content. And in practice, you'll realize that these very large number of very tiny reads and writes end up being substantially slower than just reading the whole object. So you end up getting a large amount of network traffic to enable you to do processing in any of these applications. And an interesting thing is if you walk into a large scale data center and like physically walk into the data center, you'll see that physically, in terms of the actual floor plate, there's probably about 40% of the floor plate which is used for data storage infrastructure. And there's about 40% of the floor plate that's used for all of the compute infrastructures, which tend to be carved in a whole bunch of little islands that are instantiated on demand. The other 20% is effectively like networking infrastructure and other like basic plumbing. So the storage infrastructure in reality is larger by a crazy amount than any of the individual compute islands. And right now we're using it for just storing data and moving it back and forth, which is great fun if your passion in life is selling networking gear. But that's not our passion. So what we want to do is be able to take this data and get you the results, not 10x faster. Like people in Silicon Valley wax about 10x all the time. That's great. Yeah, but like we want 100x faster. Like, because the reason people say about 10x is that in reality, most of the time, the portion of the problem that they're working on isn't the full problem someone wants to do. It's a portion of it. And if you have something that's a 20% problem and you don't accelerate it by 10x, it's probably not going to be measurable to the people that are looking at the problem. So we're taking a lot of these big data analytics where you have to load, extract, parse the right subset of data. It's not all the problem. But if we take this portion of the data set, make these operations 100 times faster, then we can provide a substantial performance acceleration at the next level. But see here, if you're able to do the selection aggregation and only return the data, which is typically like 1% or a couple percent, you're able to get a substantial reduction in network traffic. You get a much more real-time feed of the content that's going to be analyzed. And how does that translate into a classic security information event management type thing or natural language processing? We got a set of data. We work with MIT and Wisconsin-Madison on some data from basically the star schema benchmark. And we run a sequence of queries, so like simple selections, aggregations that were used in them being able to run the star schema benchmark based on like the very large tables. And for these simple, like literally using the S3 select API, which is a form of how you can do predicate push down to an object store, which like Amazon did wonderful work in saying you could use this API. Like we made the storage system so it is semantically aware of the content, and this enables us to achieve it 100 times faster, measured. So now I'll come back to how, but the next step would be like, okay, Skippy, you did this 100 times faster. How much does it solve not your problem of a simple selection aggregation? What if it's a more complex query? So work with Apache Spark. So we have a plugin. So it's effectively a S3 select connector. So Databricks, which controls Spark, does have an S3 select connector for Databricks, but this isn't widely supported by Apache Spark. So we have effectively we're working on, we'll probably release a improved connector for Apache Spark. And for Star Schema Benchmark 1.2, then this actually delivered a 5-fold total performance acceleration. And the reason, so wait, how'd you go from 100x to 5? Well, in this area, it was 80% of the problem. So classic Amdahl's law, you take 80% of the problem, whack. You take it down by a factor of 100. You're still left with the original 20%. Like 5x on a more complex query, it probably does not suck. It's a pretty dramatic performance improvement. And we did this on like literally a very tiny cluster on instances run on S3. So even though it's this level of acceleration, like, and we generally scale with size of cluster, you're not going to get at this level a dramatically higher acceleration, because once you've squeezed out to like 1% of that, the 20% dominates. So even if our cluster size at this test was 10x larger, like, and we performed the selection filters like 10x faster, it's not going to give an application level benefit of another significant order. So let's say, like, what did we do and what's different? And people have different things for how you'd have data storage and what are some of the problems and why the classic approach is not really working. So your classic resiliency 101 for data storage, like RAID, erasure coding, these things have been around for like decades, like many, many decades. And you step back, a lot of the problems in the computing industry, when people say like things are this much faster, like a factor fold change doesn't in fact make anything interesting. If everything changed at the same rate, it's just like going to the store and paying pennies instead of paying dollars. it might be great fun, but like the clerk will just get annoyed and say, like, just pay with your credit card. Like it's really no different. The interesting thing is that the relative change of different aspects of the system. So 30, 40 years ago, the relative cost of gates versus IO, like on chips. IO, particularly like go back to like the original stuff with Los Alamos that was shown earlier in this thing. And they said like people that were making some of these computers, gates were horrifically expensive. Wires inside this thing were relatively cheap. They hired armies of small women to help wire wrap things in computers. The reason they got women is, statistically speaking, women were physically smaller and able to get into tighter spaces to wire wrap these things. Like if you could train mice to wire wrap things, I'm sure they would have preferred to hire mice because they can tinier spaces. So, what's changed over the last 40 years? IO, relative pins on a chip, like those are actually very expensive right now. Gates are so bloody cheap. Like you get new chips like your phone, like they drop another gigabyte or so of memory like on a die because like they had nothing better to do with that space on the wafer. Like gates are really cheap. Classic RAID erasure coding, it's a simple ECC code optimized for just moving lots of data through with a very efficient algorithm. Okay, it works. It's proven. So let's look at this for like classic data. What if you have a table? So it's a simple table, like a number of SSDs, everything's like nice, uniform, even sizes. You can do like a very simple erasure code, bang the data through, it's completely protected, proven for decades. What's wrong? I don't know, like it's data, we want to analyze it. Like your data got chopped up into random places, cut off in the middle of things. And some portions of critical data are in one object, some portions of it are in another. Like the data you need to know what you're dealing with is like not anywhere in particular. So one of the reasons some people say, like if you're just storing the data, like you could just treat it like an amorphous blob and you just pick it up and move it because like networking is fun. Like I used to sell networking gear and then I would completely agree with you on that. But we're looking at how do we analyze data. So we looked at this problem at AirMettle and we said, we don't want to do that. We want to make the system dramatically faster. So what's the problem here? Like many cases that came up earlier in today's talks, people are looking at what is a semantic knowledge? And so how do you look at the data and like, how do you infer what data you should read? It's like some things are much better if you don't have to fake it. So we think it's much more important to look at the high level APIs that people are trying to do and what kind of analysis do you want to do? Can we make this operation of how do we lay data out like under the hood, not expose users? I mean, when you go to meet somebody, like you don't show them, here's my x-rays, here's my MRI scan, and like you present yourself as like you. So how do we hide this from the users and make it usable? So we looked at this for a way that under the hood, we're going to store the data for efficient processing and protection. So the reason that you could not do true in-place parallel distributed processing is you lack the semantic knowledge. So when we store data in our storage system, like data comes in, it streams through. It has to. You have to partition the data so you can efficiently store it in a parallel distributed manner so that you don't have hotspots on reads. So I mentioned earlier about these chips. They're enormous right now. They have so many gates. They have nothing to do. Like you might have seen some stuff on the news where people are worried about like, what happens if AI is going to come out and kill us all? Why? Because it's bored. It has nothing to do. It's sitting there all day. So what do? When data comes into our system, we look at it. But we are not looking at the contents. The contents for our purposes are irrelevant. We have no idea what anybody might want to do with the data in the future. What we can look at very clearly is what is the low-level structure of that content. So in this case, this is basically looking at something like Parquet, but Parquet, JSON, you have like, and we even support like things like MP4 and gzip CSV, gzip JSON. How can we look at the contents and say structurally, semantically, what's the boundaries of the data? And can we take advantage of that so that we just store the data? It's like if you take data on a classic thing, it's like taking like a piece of bread and taking your favorite spread, whether it's peanut butter, cream cheese, butter, and just get a nice straight blade and make it nice and smooth. In our system, it's like chunky peanut butter. Like it's a little chunky. We had a little bit of overhead. This is very much not to scale. We're typically adding 0.1%. It's practically nothing. In fact, with overhead on data protection, you'll never see it, but it's not uniform. So our erasure coding system has to deal with the fact that the data blocks are like not consistent. So this enables us to do fully distributed parallel in-place analytics. And for many common applications for security, information, event management, logs, telemetry, you're looking for things that you're extracting well under 1% of the data. We do all that reduction before they touch the wire. So how do we take this to multidimensional data? This is the focus of our awards under NOAA. So multidimensional data is a wee bit more complex than that. Like it's not like a nice, simple, like unrelated set of things like JSON line. It's a complex data format. So like they're arrays. And you still have to do things. You not just have to do simple selections, you also want to be able to do aggregations on these. And so how do you apply those techniques we had to multidimensional data? So we've been working on this for a bit over a year now. And like, in effect, you can say that conceptually, we're effectively looking at this multidimensional data and like breaking it up, I'll be quick. It's looking at this multidimensional data and effectively looking at lower order dimensionality so we can partition it into nice clean planes. And we look based on the size of the data and the structure of the planes so that we can break up this data for analysis. And then the queries are effectively like a more complex form of SQL. We look at particularly some large NetCDF data. We have the coordinates themselves, and we have the data variables. We effectively have a target partition size, and we can basically structure data on this. Obviously, there's key challenges, like how is the data, like how can we manage the data so it's transparent externally? But internally, we break this up for the actual analysis piece. HDF5 doesn't have a reentrant library, so we had to work around that. We did it only for analytics because we're doing analytics, we're not doing edits or writes. How we're extending this going forward is we're adding the ability to do regridding in place. So you can rescale the data. Instead of just rescaling it for visualization, we're looking at the ability to also do things like min, max, standard deviation. So you can look for things like weather fronts, risk of hurricane. And so we're looking at large data sets. They're trying to extract semantic meaning, give a high-level API for here's what we want to do. Where do we want to extend this? I want to add hierarchical support for true HDF type objects, including things like satellite data, and add the ability to run literal AI models, user-defined in place, pluggable. So this work has been sponsored by support from both the National Science Foundation and National Oceanic and Atmospheric Administration. So if you have large data sets that need analytics, please talk to me and my team.
Oh, Alexander has a question.
Yep.
Go ahead, Alexander.
Alexander?
Yes, so these graphs that you show, especially about NetCDF4.
Yep.
So, so this partitioning that you do, how is this different than chunking?
It's done completely internal. It's not exposed to the user. You can say it's conceptually similar, but we do it under the hood. Like the overhead is just a fraction of a percent. like the client, none of it's exposed to the user. So it's like,
That's the same.
yeah, it's probably similar, like, but we can do parallel analytics on the chunks.
I mean, that's good.
Yeah.
But it, file format wise, you sounds like some of the chunking operations that are already available in HDF5, and also sounds like some of the column store optimizations that are running around in other file formats too. So this multiple ways of sharding up the data and spreading it out in a much more semantically meaningful way has been attacked hundreds of times.
Yeah.
You know, so it's interesting. I'm curious what more than 20 minutes of information would have.
So, yeah, I mean, happy to talk at length.
Yeah.
So,
in short, the sharding is focused on optimizing parallel processing as you do. It's not just how to optimize the store, it's how to store it to be able to.
I've been telling people about chunking for 20 years, right? It's like, pick the format you're going to do the most IO on, probably reads, and focus on making your chunks optimized for that behavior. Cool. I mean, there's more to it, right? You guys are doing more than just like next source behavior. But fundamentally, it's very simple.
I mean, there's some conceptual similarities, but from the user perspective, the data is no different than the way they wrote it originally. So they completely can't tell. Yeah.
Often.
And point of all, everyone's attention to one of the slides there that you have, where it shows objects metadata in red and then internal metadata in blue.
Yeah.
That's an artifact, and a good one, by the way, abstraction.
Yeah.
And we have layer upon layer of abstraction in the IO stack.
Yeah.
It's come from every layer. In order to reduce its abstractions to the layers above, introduces metadata below the stack. It's exactly the way the TCP/IP stack evolved over time. And it allows us to have a very clear separation of concerns for each technology that involves. I just wanted to call that out.
Good software engineering designs.
We'll have many more discussions. So it's time for our next call. On concurrent multi-threading in HDF and NetCDF4. Of course,